As we have learned in the previous subchapter, the use of high-temperature storage systems in solar technology is a success story. But high-temperature storage systems are also interesting for other applications. On the one hand, such storage concepts have also been used successfully in the process industry for many years. And on the other hand, there has recently been an increasing interest in the combination of heat storage concepts and high-temperature power-to-heat applications. But first, let's turn briefly to applications in the process industry. Here we can find many years of experience with ceramic storage material. For example, in the blast furnace industry, where the heat from blast furnace gases is temporarily stored in reactors lined with ceramic bricks. The stored high-temperature heat is then used to preheat the fresh air that is fed into the blast furnace. Temperatures of up to 1300 degrees C are achieved in this process. However, the ceramic bricks are storing the heat here only for a very short time, so they are used more as a kind of regenerators. Ceramic bricks are also used in the regenerative thermal oxidation for cleaning exhaust gases, such as they are used in the solvent processing industry. The use of ceramic regenerators, usually honeycomb bricks as shown here in the figure, allows a very high degree of thermal preheating and thus high energy efficiency. One regenerator is used to preheat the exhaust gas upstream of the combustion chamber, while another regenerator is used for heat recovery. Periodic switching then takes place between the two regenerators. In this application, the ceramic is used at about 800 degrees C. From these two examples, it can be easily seen that solid materials have been used for a very long time in the process industry at high temperatures, at least as short-term heat storage. As the energy transition progresses, the need for electricity storage continues to grow. In this context, another application of high-temperature storage has been gathering interest in recent years, especially in combination with power-to-heat. Power-to-heat has so far been more familiar in widespread applications in the low-temperature range. Here, in a low-temperature power-to-heat process, heat is generated from electricity according to the immersion heater principle. In this process, a resistance heater is immersed in water, as known from household water boilers like shown in this picture. The heater is operated with electricity peaks or electricity surplus from the grid. It can thus contribute to a fast balancing and thus stabilization of power grids. These kind of grid services are usually specially reimbursed. The heat generated in this way is then stored temporarily in hot water tanks or fed directly into a district heating network. In Germany, there are already more than 30 power-to-heat plants in the megawatt class in operation. The largest, with 120 megawatt of heating capacity, is located in Berlin. It was commissioned in 2019 and replaced a former combined heat and power plant. Converting electricity into low-temperature heat results in exergetic downgrading of the energy. Therefore, it only makes sense if the power cannot be used elsewhere and thus can avoid the shutdown of wind power plants. In recent years, however, high-temperature power-to-heat plants have been undergoing extensive development. The idea here is to generate heat at a high temperature level so that it can be converted back into electricity in a classic thermal power process. High-temperature heat storage is then used for storing the heat for a certain period. Such concepts are also called Carnot batteries, named after Sadi Carnot, one of the founding fathers of thermodynamics. The operation of power plant process from a high-temperature storage unit is already familiar to us from solar thermal power plants. For use as an electricity storage unit, the collector field in which thermal energy is directly generated is replaced then by a kind of large-scale immersion heater, as can be seen here in the picture on the bottom. As described in the previous chapters, utility-scale storage systems have been successfully in operation for many years. In most of them, the two-tank liquid salt storage concept, as shown here in this graph, is used. As already mentioned, such liquid salts can be operated up to 565 degrees, sufficiently high for the operation of power plant steam turbines. In principle, it would also be possible to retrofit existing coal-fired power plants that will have to be shut down in the next few years with such a storage. In this way, they could be converted from coal-fired power plants into CO2 neutral storage power plants and thus continue to use at least a part of the existing infrastructure. However, for most modern coal-fired power plants, the salt temperature is not sufficient to operate them at nominal capacity, as they run at slightly higher temperatures than 600 degrees C. Therefore, other approaches are being investigated involving alternative storage technologies that are already known from other solar power applications. As already reported, higher temperatures can be achieved, for example, with a solid storage system such as the one used in the solar tower Jülich. As described in the previous chapter, concentrated solar radiation is used here to heat air to about 700 degrees C, and the hot air is then stored in ceramic elements. The ceramic elements used there are similar to those used in the regenerative thermal oxidation plants. To use this storage as a Carnot battery, the solar part is replaced by an electrical heater. While the temperatures that can be achieved in this way, integration into the most modern coal-fired power plants is also possible. A first demonstration plant using this technology was commissioned at the Solar Institute Jülich in 2021. In this facility, the aim is to operate the storage even at 1000 degrees C in order to extend the possible application area for such concepts. The system consists of an electrical resistance heater with an output of 360 kV that heats air to 1000 degrees C. The ceramic storage tank has a capacity of 1.4 MWh. To be able to utilize the high temperature, a two-stage electricity reconversion was selected. The high temperature is converted into electricity in a Stirling engine, in which the air is cooled down to approximately 500 degrees C. This heat flow is then further utilized in an organic Rankine cycle plant for further electricity production. In order to achieve a high overall efficiency of the stored heat, additional useful heat is extracted from the turbine at about 80 degrees C for heating purposes. The overall efficiency of this concept is therefore in the range of 80 to 90%. Alternatively, the storage could also be charged with waste heat from an industrial process. Instead of a two-stage power generation during unloading, the high-temperature heat can also be used for industrial process heat applications. Therefore, the storage concept can also support the defossilization of the process industry. As this example shows, this storage concept can be used multifunctionally, hence the name MultiTES, the multifunctional thermal electricity storage. In this slide you can see two photos of the plant. On the left you see the storage unit in blue, which is installed outside in front of the lab building. The trunk is the pipe in which the hot air is supplied. The storage tank is packed with the ceramic bricks shown before. On the right side you can see the building from the inside. In the background, in the rectangular duct, is the electrical resistance heater, and in the foreground is the organic Rankine cycle system with the evaporator and the condenser. The electrical efficiency of this demonstration unit is rather low due to the small heat engine used here. The ORC has an electrical efficiency of only about 18%. For larger applications, steam turbines can then be used which have much higher efficiencies. A steam turbine is already used, for example, in the ETES experimental plant by Siemens Gamesa. The storage medium used here is volcanic rock, which is a natural product. The storage therefore promises to be very cost-effective. Unlike ceramic storage systems, however, there is so far no long-term experience with this material. There is a risk that the stones will eventually break down as a result of the thermal cycling. The long-term stability of the volcanic stones has still to be proven. The storage is only operated at 600 degrees C, only slightly higher than the widely used salt storage. However, with an electrical output of 1.4 MW during discharge, the plant is the largest Carnot battery built in Germany to date. There is no heat extraction here, so the overall efficiency is limited to the electrical efficiency of the steam cycle, which is well below 40%. A higher electric-to-electric efficiency of up to 65% is promised by the concept of Malta. This is realized by using a heat pump process based on the Brighton principle instead of a resistance heating. This requires, besides of the heat storage, also a cold storage on the cold end of the process. A prototype of this system has not yet been reported. The presented 3 examples are just a selection of the current developments in the field of Carnot batteries, but they outline the current field of research and development very well. This brings me to the main takeaway messages of this chapter. Thermal storage represents a low-cost, well-proven option for energy storage. It is a relatively simple technology and a wide range of design variants and options exist. Ceramic-based high-temperature storage systems have been used as regenerators in the process industry for many years and are a proven storage material at temperatures of 800 degrees C and higher. Salt-based high-temperature storage systems are successfully used in solar thermal power plants to decouple solar supply and electricity production. Many such plants are located in the world's sunbelt. In the future, there will be an increased coupling of electricity and heat sectors by power to heat and power to heat and power. For these purposes, many research groups are working on the development of Carnot battery concepts. The use of cogeneration by a Carnot battery, as applied in the multitest concept, promises high overall efficiencies and thereby a high cost effectivity. An increase of the electricity efficiency is possible by using heat pumps, see for example the Malta concept. This brings me to the end of this chapter, in which I have introduced a variety of applications for high-temperature heat storage solutions. In addition to batteries for pure electricity storage and hydrogen as long-term storage, we will see such thermal storage concepts more and more on the market in the future, especially if the defossilization of the heat sector is pursued seriously. Thank you for watching these videos on high-temperature thermal energy storage.